coming to this week's energy seminar. It's probably the last seminar this semester in our series. And today we are very glad to have Professor Casey Kung from Kansas, and he's going to tell us about the aspects of next to minimal universal actual dimension models. Thanks.
Yeah, thank you. I hope I didn't bring cold weather with me yesterday. Yesterday actually was hot, but it's cold now. I hope I don't actually bore you too much with my talk today, because some of the material that I will be presenting to you today is a little old stuff. But a lot of people were asking me whether this particular model that I worked on in the past is ruled out or not because of the great LHC performance. So I'm going to give you that answer, and that's going to be only one slide. But just to get to the final answer, I need to give you a little bit of background. So for some of you who have worked on extra-dimensional model, please bear with me, although I have a lot of slides over here. So what I'm going to do is I'm going to just give you some background on this particular model called the universal extra dimensions. Here, universal simply means all the standard model particles are allowed to propagate in the extra dimensions. And I will consider a very simple model, 5-dimensional model, and I may comment on the 6-dimensional model. Basically, I will focus on the two aspects of this model, collider and the dark matter. And then I will show you current bounds on this model. Then, since things are feeling squeezed, just like a supersymmetry model, and I will present how to extend this minimal model, including more parameters, so you will have a broader parameter space. Well, probably you have seen this chart many times, but unfortunately, I just brought this one just to compare CMS chart and Atlas one. It turned out Atlas does actually a little bit better, just showing this summary. I know A&M is affiliated with the CMS experiment, but just looking at these two, right? This one has a little bit better information in general. But bottom line is SUGI is getting the scale. SUGI scale is getting higher and higher, not to be excluded by LHC experiment. Maybe there is some gap over here, then you can probe maybe interesting signature that may fall into this gap and then has not been seen by LHC until now. But it is very hard to hide supersymmetry, and there are a few proposals to do it. But the truth is actually scale is getting higher and higher and higher. That is actually simply true. And then CMS or Atlas also look for non-SUGI models. And some of the external dimensional models are listed up here. Again, their scale is also getting higher and higher, pushed up because of the LHC performance. And the model that I'm interested in this talk is a universal extra-dimensional model without the gravity. So I won't address anything related to gravity. Here, the UED and some of the analysis actually relevant for this particular model. But unfortunately, officially no analysis has been done in this particular model context. But a lot of actually bounds that we can obtain from supersymmetry is still applied. We can get some rough idea what should be actually bounds on this particular model. So just I think top is a little bit cut. Okay, I can still see some at the top over there. So what if there is an extra dimension? Suppose we live simply in 5 dimensions. So then we know this momentum dispersion relationship should be extended to this expression, the x, y, z, and suppose this py, y is extra dimensional coordinate. Then simply this Einstein's energy momentum relationship can be extended this way, including the extra momentum along the new coordinate system. Then going further, if you assume the extra dimension is circular shape, then this momentum is going to be quantized from the periodic boundary conditions. Therefore, the corresponding momentum here can be expressed in terms of some integer divided by the radius of this circular extra dimensions. So from the boundary conditions here, periodic boundary conditions, actually the conclusion is that this momentum along the extra dimension is going to be proportional to integer divided by the size, the radius. So then taking this guy, put it in the original equation, we get this equation down there. Then experimentally, we know how to measure the energy of some particle, and also we know how to measure the momentum of this particle. The difference between the energy and the momentum is going to be interpreted as mass. So in this case, there was actually mass, but there was something else that comes from the fixed component. In this case, the fixed component of the momentum, which comes from the extra dimensions. So this momentum comes from the extra dimension can be interpreted as a mass of this particle. So that's actually basic bottom line. And if you have some particle sitting in the extra dimension in a small area, small confined area, we know from quantum mechanics that this particle cannot have, with the uncertainty principle, it must have some non-zero momentum and so on. So that's exactly the same as what this guy is. Just as an example, just as a quick brief start, suppose we have a scalar field in the 5 dimensions. So let me write down simple massive scalar field of mass m in this way, and the y is the extra dimensional coordinate. Then assuming the extra dimensional circle, we can actually expand this extra the phi field, big phi, in terms of Fourier mode, in terms of exponential functions. And this exponential function satisfies this simple relationship. And this, if you multiply with 2 basis functions and integrate over the extra dimensional coordinate, then you get Kronecker delta. So using this relationship, actually you can try to integrate out this unknown degree of freedom, which is the extra dimensions. Then you get this relationship, this equation here, this Lagrangian. So then, as you see, this coefficient over here in the quadratic is actually the mass term that we have seen earlier. So what I'm gonna do is, before I get there, but then there is actually a problem with this circular extra dimensions. If you extend your space-time symmetry from 4 to 5 dimensions, or greater than 4, including 5, then it is difficult to, I think it is impossible to achieve the 2-component chiral fermions which we need to reconstruct, to construct the standard model Lagrangian. So you need to do something to get these chiral fermions. And also, if you look at, if you extend your space-time symmetry into 5 dimensions or greater than 4, then there is an extra component, which is the 5th component of your gauge multiplet. That 5th component plays a role of a scalar field in terms of 4-dimensional point of view. Then you have to address why actually we have so many scalar components in this extra dimension. So if you don't want these guys, then somehow you need to come up with a method to get rid of these things and also introduce the chiral fermions. So what has been done in the past was, instead of actually looking at the circle, you introduce extra symmetry, which means the half of the top portion of this circle is identified with the bottom portion of this circle. So you import the Z2 symmetry. So then this circle looks like a line. It is actually not a line because this guy still remembers this original symmetry. But because of this symmetry, this top portion is identified with the other guy. So it looks like a line segment with this periodic boundary conditions. And this guy is called S1 over Z2. Then by having these two, and you have you can impose certain boundary conditions on these 2 fixed points, and then you can achieve these 2 things. So then let's repeat the same thing what we have done earlier. So let's write down the scalar field on this interval. So that my action will be integrated over the 4-dimensional space-time, also integrate over this extra dimensional coordinate. Is a potential, is some generic potential including mass term. So then, as you know, this variational method gives you equational motion. But then to get the actual equational motion, there is always a surface term, boundary term associated with this guy. Then requiring local symmetry and the local field theory in 4 dimensions, we usually ignore this guy to get the equational motion. But if you think about it, our assumption on the extra dimension was it's supposed to be finite, so it's difficult to get rid of this guy. A way to get rid of this guy is actually impose special boundary conditions on this to fix the point. So in this case, if you require these Neumann boundary conditions, such as the derivative of this field vanishes at the boundary 0 or pi r, then this term is gone, then you get normal equational motion. So with these boundary conditions, actually you can expand this pi scalar field in terms of Fourier mode. In this case, due to these boundary conditions, there is no sine mode appearing. So only the cosine mode is going to be appearing in this expansion. So what I'm going to do is I'm going to copy standard model Lagrangian and write down this standard model Lagrangian in 5 dimensions, but assume the fixed component, the extra dimension is going to be is going to have this shape S1 over Z2. And then I'm suppressing the flavor indices. There's a lot of flavor indices going around, but I'm not writing them down. So then, action the Lagrangian is given. Action is given. So I'm going to integrate out. But to do it, I need to expand this each multidimensional field in terms of extra-dimensional coordinate, and using certain boundary conditions, usually or more Neumann boundary conditions. And then I have done already expansion here. And then the corresponding covariant derivatives are defined in this way. The one thing that is interesting is that this Q is supposed to be SU2 quark field, and the U and D are SU2 singlet quark field, the U for the up quark and the down type quark, and the lepton doublet and the lepton singlet. And this guy actually expanded in terms of both cosine and the sine mode, but there is always associated the projection operator as a coefficient over there. As we will see later, and this guy actually turned out to be a left-handed, although this guy is actually has a left-handed chirality, this guy is right-handed chirality, and then we'll come back to this guy later. And then with this expansion, with the covariant derivative, we put it everything over there, and then do the integration. Then, as we saw earlier, exponential functions, basis functions have some interesting orthogonality relationship. In this case, basis functions are sines and cosines. There's a bunch of these Kronecker deltas appearing in this orthogonality relationship. With this relation, you can get effective Lagrangian. So you can take a look at it. It's much simpler than supersymmetry model. This is very standard, very easy integral that you can. It's just complicated because there are many terms, but it's very easy integral.
Excuse me.
Yes.
I think this one, if I remember, maybe this is not you impose the boundary condition. Maybe we understand that this way because like a gauge field, A mu, transformation of the y go to minus y is like A phi is like partial y. So that's the reason they go to minus sign, get the additional minus sign. Not like but A mu is same sign because partial mu is invariant.
Sorry, I didn't understand your
Okay,
point.
what I say is that you have two symmetries.
Yes.
Now, the gauge field, A mu and A y,
Yes.
transform
A
like
y.
partial mu and partial y.
Yes, yes,
And because A phi transform like partial y,
yes,
for y go to minus y, they change the sign.
yes.
So this will go to sign. That's
Yes.
what I understand why
Yes,
it's
yes,
sign
yes,
is
that's
this way.
actually that's the same thing. Yeah, that's the same as the way I impose the boundary conditions. I think they are equivalent.
I think that if you just impose boundary condition, you can say I can impose B mu, A mu. In principle, I can, if you just from pure from boundary conditions.
Yeah, but there is also the similar boundary condition for the fifth component, the gauge field as well.
Yeah, what I say is that if we pure boundary condition, you can say I impose A mu, also like A phi is the same. But
Yes.
this way you understand they definitely not different.
Yeah, they are different, yes, in terms of four-dimensional volume. Okay, so
Okay.
can I take it as a comment or
Okay.
was there a question in there or just comment?
Just comment,
Okay.
because that's what really what I understand is business.
Okay, thank you. So, yeah, after we are done this integral, we get this whole Lagrangian, including standard model Lagrangian, standard model terms. This is just a quick summary. So each standard model has an infinite number of so-called Karuja-Klein partners. So for instance, for electron, there is infinite number of electrons coming out, but the only difference is actually mass. But then all these new particles, for so-called the Karuja-Klein particle, have the same spin as the standard model particles. But for fermion, we know the fermion has two chiralities, two helices, left and right. So this guy, in the standard model, this n equals 0 mode, we interpret this guy in the standard model particles, or the high order KK mode, the n equal to non-zero mode, are interpreted as the new particles. And all of these guys are so-called partners, KK partners. But in the standard model, in the doublet, as with the doublet form, there is only the left-handed sector associated with this guy. And for the singlet, in this case U for instance, there is only the right-handed guy. So from the boundary conditions, these two guys actually disappear. This guy actually do not appear in the model. And the left-handed U core and the right-handed U core, these two guys actually marry each other and then giving the master. But for the KK mode, in fact, these guys actually give you Dirac mass, and these guys actually give you Dirac mass as well. So there are actually two KK partners for each standard model fermion. So for quark, there are actually, for quark, standard model quark, there are two kinds of KK quarks associated with the SU2 doublet, and then the other guy associated with the SU2 singlet. And then with the comment that we had, this A field has a fixed focus 5 components in total, but in the standard model, we don't have actually 5th component, so we get rid of this guy, and we get only the 4 components of the gauge field. But on the higher KK mode, in principle this guy can exist, but it turns out actually all these guys actually eaten by the vector partner, and this guy actually become massive, and then become having this mass. And also, since these two guys will marry each other by a Higgs, in fact, this quark doublet and the quark singlet guy, they have off-diagonal terms that appear in the mass term. So this guy actually may be important in the KK top section. Let me skip this one. And another consequence is that all vertices at the tree level satisfy so-called KK number conservation, which means this simply illustrated by this equation here. Here 0 means the standard model, and then 1 non-zero integer is actually KK mode, mu particles. So simply this number conservation says that if you add any of these two, for instance, 0 plus 1 is equal to 1, so therefore this vertex is allowed. But 0 plus 0 doesn't give you 2, therefore this vertex is not allowed at the tree level. In the same way, if you add this 1, 0, and the 2, you don't get actually the other guy by adding the 2 of these things. So therefore this guy is not allowed either. So this guy is just a simple consequence of the momentum conservation along the extra dimensions, and or mathematical. If you look at the previous slide, remember there was a bunch of canonical delta functions appearing. That's actually result of that is actually give you this kind of relationship. And also there is something called the KK parity, and the KK parity is assigned as a -1 to the power n for each KK particles, and this is always conserved even at the higher order by construction. You can break KK parity, but by construction, the way I have done earlier actually preserve the KK parity.
So,
and then, yes.
So KK parity is just imposed by hand, just as R parity.
Yes, you can consider that. So by construction, as I said, in the standard model, the way I have done is just a copy of the standard model Lagrange in 5 dimensions, and then S1 over D2. But that's by construction, it is actually embedded, but you can break it. And then in fact, yeah, I will maybe comment on this guy later on. So,
And breaking it does, I mean, just looking ahead, does breaking it have problems with the usual problems in supersymmetry and the proton decay and all them? Are there associated problems
no,
here?
in this case, this is a non-numerizable model,
Okay.
and there is always cutoff, and cutoff is not as large as the Gus scale or SUDI scale. This cutoff might be 10 TeV, 100 TeV, even 50 TeV or so. So we don't really address proton decay or those kind of things. So this guy only has the implication of the collider side, for instance, dark matter, for instance. We don't have dark matter in any case. Collider, the KK parity is not conserved. You can singly produce some of these particles. Yeah, other than that, and also if KK parity is not there, the electroweak precision, you can get a strong constraint from there. So it's good to have this, although it's put it by hand in some sense. And all these new vertices are exactly the same as standard model couplings up to some normalization factors that we can calculate. So just once again, quick summary. The universal here meaning simply all the standard model particles in the flat extra dimensions, and this is one of the simplest example of the extra dimensional coordinate. And then you can get a whole KK tower at the compactification, and there is a KK parity, so you can address some issues with dark matter. Since this guy has a KK parity, you have to produce other KK particles. You can singly produce even particles. I'm not going to show you how to calculate, but then there is oblique corrections that you can calculate. This is just a standard calculation. Since now we know Higgs mass is fixed, that gives you actually one constraint. So by taking 125 GeV Higgs mass, actually you can get roughly 550 GeV on this inverse radius. That's the very roughly. Actually, it turns out this line is equal to 20 GeV. This was done actually more than 10 years ago. But at that time, before Higgs mass was a parameter, then this overlay correction actually, the numerical value changes as a function of the Higgs mass. So the argument at that time was that the KK scale, 1 over R, can be as low as 300 GeV if Higgs mass is as heavy as 900 GeV, but we know it is not true anymore. So to to address this electroweak resistant data, this 1R needs to be heavier than around 550 GeV or so. That's the first boundary we see by measuring the Higgs mass. So this is the left plot shows you the mass spectrum of these new particles at the level 1 for the first KK particles after electroweak symmetry breaking. So this guy is actually very degenerate, and a group of people here, the people here have calculated the RG running between the cutoff scale and the electroweak scale. That actually broadened up a little bit, but because the cutoff is actually very low in this particular scenario, unlike the supersymmetry, you have enough range between the very large and the electroweak scale, so you have enough room to increase the masses of these particles. You have a broad mass spectrum. But this guy is very short in the RG running. So it turns out that even if including these relative fractions, things are actually still degenerate. And this plot is made for this example 500 GeV. It turns out in that particular scenario, assuming certain boundary conditions at the cutoff scale that these people have done, basically they assume there is no threshold corrections at the cutoff scale, and this mass splitting is completely given by the RG running between the two scale cutoff and the electroweak scale with the vanishing boundary conditions. At the cutoff scale, everybody has a mass n over r, and on the way to electroweak scale, there might be some effect coming from electroweak symmetry breaking. That is what was shown over here. And then that particular mass spectrum in this UED is called the minimal. People often call the minimal model. Minimal in the sense that doesn't require any extra parameters, and this is the simplest example. Of course, that doesn't mean this is nature, but this is just one toy model that you can play with. It turns out in that case, KK gluon is the heaviest. So this is just as usual, because RG running gives you the largest correction, just like the supersymmetry. And then KK quarks are the next guy. And here's the KK gauge bosons, KK leptons, charges of KK. This guy is, remember there are two kinds of fermions, right? This is a double lepton, this is a single. This is something called the KK photon, which is the lightest particle in this particular scenario. So what happens is that in the hadron collider you produce strongly interacting particles, and the lepton cascade down to the lightest particle, and on the way you get a jet and the leptons and so on. In this case, the branching fraction to the leptons actually tend to be large. So what these people have done in the past was that these people had to look at the 4 lepton plus missing ET, and this was done at 14 TeV, of course. Then just pick, say, one would be like 100 inverse femtobarn. LHC can probe up to 1.5 TeV or so, for instance, but which is still valid.
So this is LHC 14 TeV.
14 TeV, yes.
And if I use the Higgs mass constraint, so where are we?
Actually,
400. Okay.
no, actually, Higgs doesn't actually contribute much in this case, because this analysis was done only for the 4 lepton plus missing ET. The Higgs mass actually does not play an important role in this case.
No, but I like.
Yeah.
He showed that the Higgs mass constrained the value of R.
It was a lower bound.
Oh, lower bound. Yeah. So this scale 1 of R, which is in this case. So there. Also, sorry, maybe I didn't mention here. There are only 2 parameters in this minimal model. So R is the 1 over R is the scale of the KK, right? R is the radius of experiment. Lambda is the cutoff scale. It turns out that this, RG running is always logarithmic. So the cutoff dependence of logarithmic, which is not huge. So that's why these people are picking one particular value. So there is a very mild dependence of lambda, but this is very small. So in that sense, effectively there is only one free parameter, which is this guy. The Higgs mass gives you around 550, depending on 500 or 600 GeV. That's what Higgs constraint is. So
that was the lower bound, right?
That's a lower bound, yeah. So 1 over R needs to be greater than 550 GeV. So this 300 GeV is all the stuff before Higgs mass was.
Yeah, I do have one question. If you have like one white, like a 500 GeV, you go to 20 TeV. 20 TeV is the cutoff? Is 20 is TeV?
No, actually, yeah, I don't know. These people have a strange parameterization. So instead of taking.
Oh, so that's 20 times that the scale. Okay.
Yes.
Okay.
Yes.
So that's still okay.
Yes.
Because usually you calculate the unitarity condition, I think 20 may be too much. Is that
Yeah,
right?
that's true.
Your
No.
breaking.
So-
The utility is after.
Oh yes,
after
utility
this
bound
table.
actually give you stronger bound.
Yeah,
Yes,
yeah.
very true.
Yes.
Sometimes it's even below 10 or
Yeah,
so.
yeah. For
Like
QCD
five.
will be much just maybe 4.
Yes,
Maybe
very
this
true.
like the number is 4.
But there are there's more than one way to calculate this cutoff scale, bounds and cutoff scale, right? So these people, you can get actually these bounds like a lambda r to be tens of 20, 30, 50 from the perturbative running of the gauge couplings. Then this guy needs to be less than around 50 or so. But yes, if you use the utility bound, it's a little bit stronger than this guy.
Okay.
Lambda needs to be, I don't remember
I
exactly.
thought
from
QCD
less than-
maybe like about 4 and 5.
Yeah, it's much stronger.
Yeah.
But also the question is whether you do this unitary bound in 4 dimensions or 5 dimensions, you get slightly different answer as well.
Oh, that's what I think. What the unitary really calculating is 5D.
5 dimensions,
So
yeah.
S1 or G2.
That was actually stronger, I think.
Yeah, it's stronger, yeah.
Oh, these are
Because
the
that's my-
AN group. These are what you did, and then there's Michigan State, Chibukula, and the Shimon. Those people have done.
Yeah,
something,
they're
and
the
then-
same group. I'm not in that group.
Oh, you're not in
My
that.
friend is Hong Jian is in.
Ah yes, Hong Jian.
Yeah, Hong Jian.
He was a postdoc.
He was-
No.
the Austin.
Austin, sorry.
He was in. He told me the result, so I know.
Yeah, you're
I know
right.
the result.
Their bounds are actually a little bit stronger
Yeah.
than the Uda. But once again, it's not clear whether which one to trust.
Can I ask you a quick question?
Yeah, sure.
So all standard model particles are KK even? Or
Yeah, zero mode by definition in this case is KK particle.
So your dark matter particle is the lightest, not the lightest UED particle, but the lightest odd?
Light is out
KK.
particle. Right? Just like a white electron is stable because that is the lightest electrically charged particle.
Okay.
Right. Just like this guy is odd because this is the lightest odd particle. So that's why this guy is stable.
So your lightest even KK particle.
Will decay into something else.
Okay.
Yes. So thank you for the comment. So I will come back to that later. So because that gives you actually interesting signature. Because one guy, even guy, can decay into 2 even guy. In this case, 2 even guy in the final state may be standard model particles. So if you can find these two, reconstruct, then you can find the resonance. Right, that is the collection. So there were, I'm skipping a lot of history here, although I have given you a long history, but until last year there were actually several papers came out, but this is the most recent one. Let's forget about 7TeV. This is 8TeV done by these people. I believe 3 of them are actually on Atlas, so they are doing follow-up study right now. So this is lambda r, and this is inverse radius. So if you take the 95 confidence level of exclusion, then this guy gives you limit around 1.2 to 1.3 TeV. So currently the ATV with 20 inverse femtobarn here actually exclude up to 1.2 to 1.3 TeV, depending on this lambda value. So it's about 1.3 TeV also. Once again, the dependence on the lambda is logarithmic, so there is not much variation along the vertical direction.
So these 3 leptons you are producing from these KK leptons?
Yes, in this case, actually they claim that instead of looking at 4 leptons, so you have 4 leptons, if you look at more leptons, or you have to pay for the branching fraction. So these people think that actually 3 lepton signal is actually better than 4 leptons.
And so these KK leptons are produced in some Brilliant process?
No, this guy is LHC, so you do the KK core production. or
Oh,
KK
okay, so
cascade.
Yeah, yeah.
Yes.
So what's the mass of the KK lepton? For this,
Once again, it
if
depends,
I
right? If you
convert-
pick the 1 TeV, all the standard KK particles are at order 1 TeV. And then there is like 20% and 30% of variation due to the RG effect.
I thought this is the WD.
Yeah, this will involve WNZ, yes, because you need to get here. For instance, this guy is the KK force, right? So you do the production of the strongly interacting particles. At the end, this guy will give you KKZ and the KKW. This guy will decay into KK leptons. When from here you get leptons, right? Leptons. So if you go through the KKZ, and this guy give you 1 lepton, when KK lepton decays to KK photon, you get 2 leptons. You do the pure production, you can get up to 4 leptons. Right. It's exactly the same as this. This is second lattice neutrino, this is chargino.
And so all the masses are close to 1.
Yeah, all the masses are close to 1 over r. And from here to the heaviest guy, it's around 25 to 30% correction.
And the exclusion bounds are very similar to SUSY exclusion bounds
Yeah,
because
it
it's
is.
just color.
Actually, it is actually very similar. The reason is that
Because of color. It's just,
here,
they all seem color.
I'm speaking here a lot of the information here, but it's relatively heavier. It's a squeezed. My spectrum is squeezed, so therefore your decay production much softer than SUSY case. However, you gain in terms of production cross sections because this guy spins are different. So generally, if you do KK quark production and you compare with the squark pair production, generally the cross sections of KK particles are generally 5 to 10 times larger.
So you're saying all these are squeezed, then those leptons are soft leptons?
Not actually very soft because at the end these guys also get boosted a little bit. Yeah, but not a lot. Yes. So even Stephen Martin's compressed supersymmetry, compared to this model, this model is actually a little bit broader than this one. But there is still, I mean, you can actually tag on this guy. Yeah.
So if suppose, so if your KK gluon is at 1.4 TeV, say, right?
Yes.
Just outside the exclusion bounds, then given this compression, what's the lowest mass you can get for your leptons, or sorry, not leptons, KK?
So for instance, 1.4, that means actually the KK photon mass is 1.4, right? But this guy doesn't get any, it gets almost no corrections. So and then this guy is about 1% heavier than that. So 1% of 1.4 is 1,000, right? 10.
All right. So it's very heavy.
So this is about 1% heavier than that. This guy is about 30% heavier than that. This guy is about 7%. This guy is about 10 to 15%. And then the roll is about 25 to 30% heavier.
And have you considered direct production of KK leptons and KK?
But those are 1 TeV, so not.
Yeah.
No,
so
but the KK, there's no reason for the KK leptons you want to.
Yeah, that's
no,
what
no.
we
Once
said.
again,
That's because of that electroweak.
Electroweak.
Oh, the electron.
right? Those guys. Once again, if you really believe, right, with this toy model, right, seriously, consider seriously, then the minimum lower bound, at least in this particular scenario, lower bound is already 550 from the Higgs mass.
Okay, got it.
Right.
Because I'm just a little bit confused.
Yes.
Usually, compressed supersymmetry maybe still can relax the bound a little bit. But here the bound is just similar to the supersymmetry bound.
Yeah, exactly. So
That's I don't understand.
That's why I was asking.
What is the bound on the compressed SUSY?
I think maybe below.
Oh, much below, because that
Yeah, it's
don't
much
feel
below.
like this
That's
1
my
TeV.
impression.
Right. I
It is
don't.
soft.
Yeah, I believe. I don't know how many the mass splitting between the heaviest and the lightest particle in that case. I believe this guy is a little more squeezed. But it turns out, like I said, the production cross section is very larger.
But
much
your
larger.
lepton PT is how much you don't know. Like,
Yeah.
So that's why I'm asking.
Yeah,
Because you have 3 leptons and all these PT of the leptons are greater than 10 GeV, 20 GeV.
no, it is easily greater than 10, 20, 30
Okay, then
GeV.
maybe it's okay, right? EV greater than 10.
Oh, I think maybe the reason is that usually you get the very not maybe relaxed amount bound because you take the simplified model. But here you have all the quark.
Oh, was
Take
it about the was it on the simplified model?
Yeah, maybe
Oh, okay.
for the compressed, you
I
can
see.
take some simplified model.
Oh,
But
okay,
here you
there-
can
there is
have all the
different-
score, all the
yeah.
heavy modes of quark
And,
will be produced.
And also, this in
All
this
the
case,
quarks.
there is a multiplicity, right?
Yes,
You-
that may be
No,
the
that's
reason.
what
That's
we're
what,
doing,
yeah, I was
right,
thinking
yes.
maybe that's the reason.
Okay, I see. Now I thought that you meant actually Stephen Martin is this particular model,
No,
the
no.
entire spectrum.
No. It's people
Okay.
always discuss this compressed. They use some simplified model, and the bound is really low.
No, I think if you consider for
But
the
here you have all
different
the-
spin scenario,
Yeah.
with exactly the same simplified model, I think bound will be stronger.
Okay.
I think because
Oh,
it's like with the exactly same mass spectrum,
Okay.
because the production cross section is larger,
Yeah.
right?
Now, also you have 20 GeV, if you have 20 GeV leptons and large missing energy,
That may help, yeah. Yeah. Okay, so we are getting closer to this phase. Okay, this was actually found. I'm not sure, maybe Tangent may not agree with this statement. So is actually the extra dimensions in some sense. So you have superfield.
I completely agree with this.
You agree?
Yeah, because theta you consider acceleration.
But that is actually part of extra dimension. That's
Yeah.
something that we don't know. In broader sense, in general sense. I mean, okay. So Okay, so you extend your field in the superfield, including this extra dimensional coordinate. In this case, this guy is a Grassmann number, although in this case it's a bosonic. So you have a certain symmetry, and in this case, higher dimensional Lorentz symmetry. You have a partner, you have a KK partner, and this guy is actually sort of a basis, the Grassmann basis. But this case, you have some depending on geometry, you can do cosine and sine. And you have a different spin statistics. You can define your action. You can find effective Lagrangian. There is associated the parity, and you can simplify SUSY model, invoking some scenarios like M-Sugura, CMSSM, and the same thing happens here. This guy has very small number of parameters. And of course, this guy maybe meaning you can invoke, of course, always change your gauge group, but it is similar. So at the end, you can get a very similar signature from the cascade decay. The squark, KK quark, second lattice neutrino, and KKZ, KK lepton, and lepton, neutrino, and photon, and so on. So it's a difficult. It's not impossible, but it is challenging to distinguish two different scenarios, looking at get the same final state. And then another distinct feature is that unless you involve your gauge group in the supersymmetry, MSSM at least does not give you the resonance structure. This is something that we had a comment earlier. The level 2 KK particles can decay into two standard model particles in the final state, so this guy can appear as a resonance. So this guy is something that can be looked for. Unfortunately, the KK parity is conserved, the number is violated. So this, therefore, according to KK number conservation, this does not appear at the tree level. So it means this guy must be loop suppressed. So you can calculate this guy, and the one, so let me, example is this coupling, effective coupling of the level 2 KK gluon to the QQ dipole coupling looks like this. There is a logarithm dependence on the cutoff, and there is this guy is to the loop version. Okay, I'm not going to explain this guy. So the best way to look for this resonance is either dijet or dilepton. So dilepton has been done. In this guy, once again, this is for the 14 TeV LHC. For let me pick 100 inverse pentagon, there was some typical luminosity that I can use easily. And this guy, picking 100 inverse pentagon of the luminosity at 14 TeV, I think bounds LHC can probe up to say 900 GeV or so. This bound is a little weaker than the bounds that you can get from the trilepton, for instance.
Why electron is stronger than you?
Just I think the cuts are different. I think I used the different cuts, and no, actually they let me see. I think cuts are different. I think I think cuts are different for muon and electron. I don't remember exactly where the difference appeared. Look at this number.
Okay.
Sorry, it's been so long. But one thing that I don't think this is the guy, but one thing that was interesting to me was that suppose this guy exists, but the CMS always emphasized muon detector is great. But this guy is a very energetic muon that decayed from heavy resonance. The muon, you have to rely on this curvature tracking information. So this guy is very energetic. You may not able to get good mass resolution.
That's why.
Yeah, that's one reason. So then, even if there is actually double resonance, because level 2 KK photon, level 2 KKZ, both of them can decay into muon and electron pair. But the muon, because of the worse mass resolution in the muon channel, you may see actually kind of distorted one Gaussian distribution instead of two double Gaussian distributions. But if you use EPEL, resolution is actually much better for very high energy. I believe it's order of 1%, probably better than 1%.
So you got to use a seamless parameter.
Yeah, same as parameter. Yes. So how can I do it otherwise? So I think this is also all the parameterization from some paper that a long time ago. It might be a little bit better than this one, but the point is that the electron will be, the EKL will be able to actually probe these two guys separately, but muon channel may be hard. Okay, finally dark matter. So this is notation is slightly different. So D is a KK photon. The reason is that the high Weinberg angle at the for the KK particle is very small. So hypercharged KK photon is almost same as the KK photon. So this the notation is different, but this is actually KK photon. There are two annihilation channels: a fermion final state and the Higgs final state. The first calculation was done by these people a long time ago, and this black curve actually gives you bounds. Taking 0.11, and this guy gives you about 900 GeV or so, 800 or 900 GeV. And then you don't want to go up, be somewhere here rather than this value. You want to be in the left side of this curve. But then the later different groups, including myself, actually calculate lots of fractions to this curve. So depending on how you actually calculate radical abundance, including resonance effect, the co-annihilation effect, and the one effect that doesn't exist in the supersymmetry is something called level 2 particles in the final state. Because level 2 particles that we saw earlier can decay into 2 standard model particles at the end. Including those kind of effects, these bounds that you can get from the radical abundance calculation can be as large as 1.5 TeV or so. And this was done in the context of the minimal UED. I believe this group have done a very good job here. So this is actually the final number in terms of radical abundance. So like I said, you don't want to be in the right side of the curve, you want to be the left side of this curve over here. Of course, you can always involve some strange scenario, and to get away from this radical abundance bounds, you can certainly do that. What I did here is that intentionally I changed the mass splitting between the KK orb and then KK photon by hand. So I assume magically this can happen from the different boundary conditions at the cutoff scale, different RG running, and so on. So then this delta parameter is the mass splitting, mass difference between the KK orb and KK photon normalized to the KK photon. And this guy is roughly 10%, 15% or so in the minimal model. And the x-axis is basically 1 over r, which is the KK mass of the KK photon. And these various curves actually shows you the different bounds that you can get. For instance, this guy here, cyan, with the dotted line here, it's difficult to see, but this line over here, this is the current LHC, ATV LHC bounds that we saw previous slide. And this yellow then is LHC rich, assuming 100 inverse Bank-to-1. This is what LHC can probe. And then this 0 and 100 is actually current bounds. And the lux bound is about factor of 2, as you know better. So it's very close to this guy, but this is a log plot. I don't think it will be very different. And this is some kind of expected sensitivity, assuming you have a Darwin and the 0 and 1 tone. And this green band here is the parameter space that is consistent with Planck, the 2 sigma band. So since this is very narrow, if you really believe 100% of dark matter is explained by the KK photon, then you have to live on this green band. And then here point is that the various techniques to find this particular model, direct detection and radical abundance, or collider, all of these guys are complementary. And this is for different scenario. So in this case, this is a minimal model, but some variation along the quark map. Okay, let me spend maybe a couple of minutes. Then I just discuss one particular extra-dimensional model with some mass spectrum. We saw this transition amplitude between the particles. But if you actually extend this model to 6 dimensions, there are some extra particles coming into the game. Those guys are called spinous particles, because if you extend your gauge field into 6 dimensions, in terms of 4-dimensional point of view, you get 2 extra scalar particles, a fixed and a 6th component. So one of the combination is eaten by the vector partner, and the vector partner becomes massive. That's why these gauge bosons become massive. But the orthogonal combination in 6th dimension actually survives as a physical degree of freedom. So those guys are called this GH, ZH, and WH and BH. It turns out, under the same assumption, the vanishing boundary condition, the cutoff scale, the you do the RT running, then you get a mass spectrum at the electroweak scale. It turns out all the spin 0 particles, scalar particles, actually get negative corrections. They become lighter than the vector partner. Which means in 5 dimensions, KK photon, vector particle was the lightest particle, But now the spinous partner for the pH, spinous particle, spinous photon, this guy is actually lighter than the photon, which means this guy must decay into the lightest particle. And then when decays, actually it decays to this one, emitting by a three-body decay or one loop decay, emitting a photon.
So what's the mass difference?
I think when this guy was 500 GeV, this was about 490, 480 GeV. So I guess it's about 20% difference, I think. But roughly. Yeah. So then if you actually calculate then branching fraction into the spinous photon and the photon is about 34%. For each fermion it's about 20% or so. So actually they are actually comparable. So either three-body decay or one-loop decay, these guys actually give you about the same. But interestingly, now KK photon is not a dark matter candidate because this guy will decay, emitting a photon. So it looks like this lightest neutrino decaying to gravity, emitting a photon, for instance. At least in terms of the signature, it is similar. And of course, there is a partner, color octet scalar, which didn't exist in the minimal model. So this is a color octet vector. This is a color octet scalar. All these scalar particles they have actually slightly, actually very different, not slightly, very different phenomenology.
So this is a color octet scalar.
Color octet scalar, yes.
Around 500 GeV.
Around 500 GeV, yes, in this case.
So electricity production we do check.
Yeah, it is actually, but we will get there. So this is also interesting. So that's why, so that's actually one of the my message at the end. Why we study this exotic, strange toy model. Sometimes you do get interesting ideas looking at the signatures.
So also this
yeah.
dielectron mass could have an endpoint.
In this case, yes, which is given by the mass split in between. It's just like a supersymmetry case. So I mean, this is almost the same as a supersymmetry, right? Just a different spin and so on. Yeah, I mean, so you can now you can take this so-called simplified model approach. What if? Yeah.
Just one second.
Yes.
Color octet is 500 GeV and lightest object is about 490 GeV. So
yeah.
mass splitting is very
Oh, I'm sorry, I spoke wrong. Sorry. For 500 GeV, this is 390. Sorry, not 490. Yeah, sorry.
Okay.
Cross,
So that's
yes.
so but within 100.
Yeah.
But maybe those, and what's the WH? That mass is somewhere in between.
It's somewhere in between.
So what's that WH? It's
This is looks like a W.
Yes, scalar.
Scalar W.
Scalar W.
And then this guy can decay into, of course, one lepton and then the two. Then most of these guys actually go through the three-body decay. Only this guy actually give you, and also this guy as well.
And that scalar W is about 350, around 450.
450 or so. Yeah. Once again, it's very compressed, but interestingly, all of these guys were actually decayed to vector partners, but now this guy can decay into the other guys, changing the decay pattern. Well, we can go through, but it turns out, I did a simple exercise. It turns out you can get lots of leptons, but unfortunately softer leptons. Still, you can say this is LHC cross-section. Multi-leptons as a function of this parameter, 1 over R. You can get actually a lot of leptons. Although this is the Pentoman, look at these numbers. So this guy actually gives you lots of leptons. Maybe you can look for 3 or 4 leptons. You can even get up to 6 leptons. Now, what is more interesting fact is that this KK photon can decay into photon plus spinous photon. Right? You can get photon. So you can look for photon plus lepton signature. The striking thing is 1 photon plus same sign dilepton. But I don't think there will be any background to that. And then unfortunately, this is just simply cross-section without any acceptance, without any cut. This is purely just a cross-section at the 14 TeV. Well, this has an interesting signature. They can be looked for. But just one more slide. What about dark matter? Because dark matter can be different. In this case, this is a pH scalar particle. So this is an annihilation channel via Higgs and Higgs finite state and the fermion finite state and so on. Because this guy only talks to Higgs, and then the dominant channel is the TT bar layer eventually. The truth is that because this guy is spin zero particle, the annihilation cross-section tend to be smaller than annihilation cross-section you can calculate with the different speeds, not a spin half and vector spin 1 particle. Therefore, if you increase the Higgs mass, which appear as a resonance, then of course we can increase the mass scale of this particle. So that's what I did here. So this axis is Higgs mass. This is required mass scale R inverse, which is this is the old number. Then you can get this contour shape. Now we know what to do. Higgs mass is 125. This guy give you a scale around 250 GeV or so. Go back. 250 GeV. Here's some area. This can be easily ruled out already. Actually, probably even at the tevatron, there is a very strong bound.
And how does the Higgs mass constrain this six-dimensional?
There is actually, thank you for the comment. So Dawn has done the actual that calculation. So the person who looked at this 60 model is Bogdan and Gustavo Bergman and Edward Thornton. They have done some quick estimation. It turns out that was greater than 600 GeV or so already. But this overlay corrections, you can always find a way to get around it. But if you take it seriously, yes, this is already 600 GeV. That's why actually we wanted to, wrong button. We wanted to rely on the Higgs resonance so that I can increase this guy as much as I can. But now I cannot do it anymore. Now you can ask, okay, there is no correlation here. But in the previous, in this case, there are lots of particles nearby. Does correlation effect actually change result? Unfortunately, no. Actually, it goes in the opposite direction. It actually reduces further, a little 10, 20, 30 GeV actually lower. So this guy doesn't help. Correlation effect, whether it's increase or decrease, that depends on the relative importance between the correlation and actually the annihilation diagrams. So in this case, actually it goes the opposite direction. So unless you do something, then 60 model is actually disfavored because of 125 GeV. So I know many of you are familiar with extra-dimensional model, but not particularly in this UED model. So minimal UED, once again, minimal here simply means the vanishing boundary conditions at the cutoff scale, and this model depends on the two parameters, 1 over R, size of extra dimension, 1 over R, and the cutoff scale. But cutoff dependence is logarithmic, so it doesn't really play a very important role. It's similar, in some sense, it's similar to CMS's and M-Sugaran model. This one has 4 or 5 parameters. But the two universal extra dimensions, since, it's not really a GMSB type, of course, right? But in terms of signature, since you can get a photon from the decay of the KK photon. So in terms of that signature, I said, okay, it is similar, but it's slightly different. In some sense, it is actually close to n equal to 2, because there is a spinous vector partner. So actually, there is a analysis to the n equal to 2. And the Michigan group, Aaron Pierce and his former postdocs actually worked on the non-minimal model by having some boundary terms at the fixed points, some terms in the fixed points. And then that's where actually you can break the KK parity. And then unfortunately, these people call their model as a non-minimal model because it's different from minimal model. But then a couple of Japanese group came up with an idea, so-called split UED. It's very similar to split SUDI. So what these people have done is that normally the Dirac mass is not allowed in the standard model because of the gauge symmetry. But if you extend the model in the extra dimension, you can actually write down the Dirac mass term for the KK fermion postulate, and assuming the coefficient of the Dirac mass is given by some kink type of structure. So then there is some term, it's not actually different from this model, but actually you can write down some term that doesn't exist in any of these guys, none of these, either of these guys. And the effect is that you can actually you can lift up the mass of the KK fermion very high by playing with this parameter. It is very similar to the split SUDI in that sense, because all those fermions are very heavy, but in this case, all the KK fermions can be much heavier than KK bosons. There is a little SUED compared to capital SUED. This is there is a paper by Yang Bai in the past, so to explain some of the anomalies in the indirect detection of the dark matter. So he extended the UED model with the one singlet. He called it the little SUED. Well, but the natural thing to do is, why don't we include the both? Then my problem was, how are you going to call it? it should have been called as a non-minimal UED by the video. But these people already called it non-minimal UED without the Berkeley method. I needed a name, so I am calling it a next to minimal UED. Well, but in some sense, this guy should have been called as, PUED in some sense. But
Or
because
AMSM.
PMSSM, PUED. Well, anyway, so I don't know how to call, but I'm just calling it as a next to minimal UED because there is a reason. Because I still, there are in principle 19 parameters I will show you in the next slide. The reason, interestingly, it was surprising to me that no one has actually included both. It's just a simple exercise. It's not very hard. Probably this is very easy exercise to many of us. But actually, it turns out it's a little bit tricky because you have to calculate the KK mass spectrum. So it's there is a little bit of a math problem with the trigonometric functions. But otherwise, it's a very straightforward work, and that's what I have done here. So here's a line segment with S1 over Z2 and the two fixed points. This is the typical Berkeley Lagrangian that we write down. But here I added this Dirac mass term. But I assume the Dirac mass term actually can change its sign when you set y to -1. This can be, there was some idea with the split fermion idea in the extra dimension in the past. Actually, the idea actually came from there. And in addition to these terms, you can actually write down the terms that are localized at these two fixed points, and all of them are over here. And in principle, all of these guys have different coefficients. Then if you count, just to avoid the flavor changing visual current, it turns out actually it's 19, which is the same as the number of parameters in the PMSSM. So this guy can be called the PMSS. The problem is that you cannot actually solve analytically. At least the mathematical doesn't give you an answer. So it's hard to solve it. So what I did was, well, there are too many parameters. So let me assume the same Berk mass and the same boundary parameters. Then you can solve it by hand. So that actually gives you a nice result. And there is also some other reasons here. If you have a different parameters, sometimes vacuum expectation value of Higgs becomes now y dependent. Actually, this itself is very interesting. So if you live on one brane, we live on particular brane, the vacuum BEV is 255, but along the extra dimension, BEV actually becomes different. So there is some phenomenological implication of this guy, but I haven't investigated yet. And there is also KK model mixing. Then there is a reason. So I said all the R's are the same, all the Berk masses are the same. That gives you two extra parameters in addition to original lambda and R. And then you can do the mode expansion. In this case, it's a little bit ugly, but this guy satisfies certain boundary conditions that exist in the original model. And you can get the mass spectrum for fermions and the bosons and so on. So here, bottom line is that the R parameter, boundary parameters, generally reduces the mass of the KK particles. But the new parameters that comes with KK fermion, comes in the KK fermion sector, actually increases masses. That depends actually sign. And I'm taking actually the negative side. If mu is positive, then the KK fermion becomes lighter than KK bosons. If mu is negative, actually this guy becomes heavier than KK bosons. So this mu controls the mass of fermions, and then R actually reduces the mass of the both KK bosons and fermions. And also it changes the masses. It also changes coupling. So the MUED, so the UED original point corresponds to 0, 0 over here. All the standard model coupling with respect to all the gauge couplings here with respect to the standard model guy is actually 1 along the line. So this is the UED points over here and here and here. So now in this extended parameter space, boundary parameters and the Berk masses, now the couplings actually change. Yeah, this has been done numerically with this wave function profile. After you get wave function profile analytically, you can get this like easy. So couplings are modified and the masses are modified. So things are actually quite different. So you can address this issue. And the idea was that if you do the Higgs precedent, if you take the Higgs precedent data, and the Belanga and this European group claim that the UED model, the bound that you can get is R inverse need to be greater than 750 GeV or so at 95 confidence level to take into account the Higgs data in this particular model context. Of course, if you do this one, you can get actually very low scale as well because you have more parameters in this. So what you and I and then Danny were playing with was that one of the distinctive feature in the UED is that since dark matter candidate is a KK photon, hypercharged gauge version, the largest, the particle that has the largest hypercharged coupling is, the right-handed electron. So this model gives you lots of leptons. So can this model actually explain the positron, for instance? You can ask the question. And the typical problem is that antiproton data, right? You have to suppress antiproton while you get a lot of leptons. But suppressing antiproton is not an issue here, because when this guy annihilates into QQ bar finite state, there is always T channel KK quark appearing. So then you can introduce bulk parameter for the KK quark, making this guy very heavy. That way you can suppress branching fraction into QQ bar finite state. So we are actually investigating this issue, and in this parameter space there is a very density contours here. So all of the white area is consistent with the point 11, and there is some reason excluded by CMS and then precision electronic data. And the question is in this parameter space any point here consistent with this positron and then antiproton data? So we are currently investigating, and we don't know the answer yet. So that depends on use simulation wizard. But one idea that we got was that maybe this bulk parameter that I assume over here was universal, just basically the same value, may not be actually the good answer, because this guy looks like our current status is it looks like this universal parameterization seems to fail to explain the positron and antiproton at the same time, which means maybe I can relax that assumption, introducing different bulk parameters for each quark generation. That actually gives you my sort of last slide. There is a tied with, suppose there is some resonance here. I call it G3. Suppose this guy talks to TT bar only, because this guy, if you include this guy, the coupling of this particular resonance to TT bar becomes very strong. Then in that case, suppose this resonance only talks to TT bar. When experimentalists look for TT bar resonance, if you look at a paper, they always produce from QQ bar. It's a TT bar resonance, but it is produced from QQ bar annihilation. Of course, we have to produce it first, right? So that means that this resonance will have a non-zero branching fraction into QQ bar again. So you have to avoid the dized bounds. So that means that you have to make it heavy, and you have to make dipole coupling small. That gives you actually small production cross-section for the TT bar resonance as well. So you have to balance these two things. But really, to claim this guy is a TT bar resonance and assume this guy doesn't have a dipole coupling, then how are you going to produce it, right? The only way to produce TT bar resonance is actually via glue here, glue annihilation. So this is one mechanism here. Glue, this guy is the top line here, top fermion line here, and you produce this guy. Of course, this guy will change it. Another way is via this one loop with the top. And as we know, without this gluon, the Landau-Yang theorem actually is violated. So you want to attach this guy, so this triangle becomes box. And interestingly, my quick estimation tells me that these two guys are actually comparable. If you assume order 1 coupling in this guy, and this is a several hundred GeV, this cross section can be as large as a several hundred femtobarn at 14 TeV. Actually, they are actually comparable. The problem with this guy is that here the statement will be that if you want to look for TT bar resonance, how are you going to look for TT bar resonance? You have to look for 4 top final state, otherwise you are not going to see it. The same way, if you want to look for TT bar resonance, you have to look for TT bar plus 1 jet, otherwise you are not going to see it. Of course, you can actually go further. What if this guy also talks to PB bar? Then there are other production and decay mode here. So, bottom line is that this Higgs 125 GeV actually disfavors this particular two universal extra-dimensional model. And then, as I said earlier, the minimal UD model is getting squeezed, just like a supersymmetry. Current bounds from ATEV LHC data is about 1.2 to 1.3 TeV as a function of the lambda. And from radial abundance, if you believe it's a thermal relic, then this bound is about 1.5 TeV. So this room, there is not much room over here. And then order of 100 inverse femtobarn at the 14 TeV can easily cover up to this guy. And you can extend these models by introducing brain terms and the bulk masses. Then you have more parameters to play with in general. Well, so why do you consider exotica? You can always there is always something that you can learn by considering these kind of toy models. So one example was this is my last slide. Thank you.
Question for Casey?
Can I see the quotations for within and
Oh,
sample?
sorry, I will test. I'm not sure whether they said it actually.
Okay.
I found this on here.
Okay.
Wait on this.
I think probably Jolie can stop.
Oh,
I think Jolie can once gave a talk, is Princeton ready for the LHC startup or something like that, like 10 years ago. And there was some, I believe, yeah, I think probably Jolie can stop. So, do you have any other question? Yeah. So one thing that one anecdote, when I participated in the PITP summer school a long time ago, school was about applied physics, and I participated as a sort of a student TA. I was helping Michael Peskin and Konstantin as a TA. So then, I don't remember. Hinsley was going over this Isazed and spin correlations and a few things. And there was actual tutorial. And he said, okay, copy this file into your own directory. He prepared already everything, and everything was saved under his account. Copy this file into your own account so they can run this as an Excel spreadsheet. And then everyone did it. And then is everyone okay? Except for one person, Witten. I tried, it complains. And they said, no, just copy this file and then into your directory. He repeated. The Witten said, I tried, it doesn't work. And then suddenly Simon said, it works for me. It turns out what Witten did was, instead of, he said COPY, file name, and his directory.
oh my God.
So then Simon said to them, I know how to copy, you don't know this. Oh, this is a big broadcast.
The last line of the I know.
And his comment, I know how to copy.